And welcome back. Hopefully we had a nice little short break there, or a longer break. Either way, we're glad to get back and continue our conversation on confidence intervals on the mean. All right, so let's just kind of summarize a couple things real quick. So if sigma is known, the standard deviation is known, then our limits for our confident interval will be found as follows: x bar plus or minus z alpha over 2 times sigma over the square root of n. If sigma is unknown, then our confidence limits will be x bar on the mean will be plus or minus t of alpha over 2 times s over the square root of n. All right? Just to kind of summarize what we have so far. Now, when we look at this, let's think about the following here, right? If we hold the confidence percentage to be the same, right? So let's just say, we're talking about a 95% confidence interval. So you want a 95% confidence interval. So then z of alpha over 2 or t, whatever you have to use, that's not changing. What if we increase the sample size? I want a 95% confidence interval. And I repeat this, but I increase the sample size n. Well, n here is a factor in the denominator. As n gets larger, that denominator is going to get larger. And so this product that you're plus or minus, that term is going to get smaller. And so if we increase n, the confidence interval will become shorter. And that should make some sense, right? A larger sample, more accurate, more elements from the population are included, right? And so we can be more confident and a little bit more restrictive in our interval. And this is the motivation behind the following theorem, where we can specify if we specify how big we want the interval to be, we can talk about then the desired sample size needed to obtain that interval of accuracy. If x bar is used as an estimate of mu, we can be 100 times 1 minus alpha percent confident. That the half width will not exceed a specified amount E. Let me just see here. So this half width, right? This is a half width, and this is half width, right? It's half the width of the interval because you do plus and minus, right? You would do plus and minus. So like, you could say, z alpha over 2 times sigma over square root of n is your half width, right? So back to the theorem. If x bar is used as an estimate of mu, we can be 100 times 1 minus alpha percent confident. The half width will not exceed a specified amount E when the sample size is n, that is z of alpha over 2 times sigma over E squared. Z of alpha over 2 times sigma over E squared. That is the desired sample size. And I'll just mention, in terms of practice, right, we are only going to try to use this, we're only using this when sigma is known. Let's not extrapolate this to the t-distribution quite yet. Only when sigma is known. Only when sigma is known, right? So if we have sigma, if we know sigma, then we're working with the z-distribution. So you have x bar plus or minus e is your desired half-width. E is your desired half-width of the interval. Let's take a look at an example then of computing desired sample size, okay? And let's just continue the zinc concentration example that we had in the last video, the zinc concentration from the last video. How large of a sample is required? How large of a sample is required if we want a 95% confidence? Well, 95%, oh boy, let's try that again. We want 95% confidence that our estimate of mu the population mean, has an interval of length less than 0.10. All right, so some things I want us to pull back from the previous example. So this uses z of alpha over 2. We're talking about a 95% confidence interval. And so we know we're looking for z of 0.025. We found that to be 1.96. We found that to be 1.96 in the last example. We also, in the last example, were given sigma was 0.3. All right. So what else we need then? E. E is the half-width. E is the half-width. All right. So what is E here? Our estimate mu has an interval of length less than 0.10. The total length is 0.1. So half of that would be 0.05. 0.05. Half of that would be 0.05. And so then n is z of alpha over 2, so 1.96, times sigma, divided by e, half-width, and then the quantity squared. And so in this case, we run that through a calculator. We find that n is 138.3. Naturally, we can't take a sample of size 180 or 138.3. So think about where this is going to go. Yes, 138 is closer to 138.3, but 138 would not be enough to ensure the proper accuracy, right? So in this case, we need to round up to 139. And that'll be an even smaller interval than length 10 because we've rounded up a little bit. If we had exactly a sample of 138.3, then we get an interval of exactly 0.10. If we took an interval, sample size of 138, our interval would be larger than 0.10. So we want 139. Sample size of 139, and then we can get a desired interval length. And this is pretty powerful if you have the right conditions to use this, because now, you know, if you're within 0.1, that's pretty good. That's probably, you know, that could be pretty good, right? Or you can specify that accuracy, right? If you want to be within 0.01, you want to be within 0.01, you want to know what, you know, that mu is equal to x bar, you know, plus or minus 0.01, right? You get to choose, you can figure out what that sample size is. You know, that's pretty powerful if we have the right conditions. Something that we're going to switch gears a little bit here and think about then is, you know, in these instances, we have what are called two-sided intervals. But sometimes we are really only interested in one bound for our parameter. One bound for a parameter, right? So what's an example of this? Like, think about the something measuring the strength of some metal rod or metal component or something like that, right? Well, you might need an upper bound. You want an upper bound for the average strength, but you really wouldn't care about the lower bound in some sense of what the average strength would be, because you might need to be ensuring, that it's at least a certain strength, right? So consider the strength of a metal component. All right. We might want to know an upper bound. But not care about the lower bound. Just one sort of potential thing, as far as, setting something up, right? And we'll take a look at some examples of this shortly. But what happens when you are only looking at one side then, right? If x bar is the sample mean from n observations with a population variance of sigma squared, the one-sided 100 times 1 minus alpha % confidence bounds for mu are, if you want an upper bound, upper one-sided bound. Let's think about this. This isn't too mind-blowing. 100 times 1 minus alpha %. When we had a two-sided confidence interval, we were looking for alpha and saying we're splitting that evenly on a left tail and an extreme right tail. But if this is just an upper bound, then I am just going to take all of that and put it on a right tail. So x bar plus not z of alpha over 2, but just z of alpha times sigma over the square root of n. If we're talking about a lower one-sided bound, then we have x bar minus z of alpha over 2 times sigma over the square root of n. Upper one-sided, upper or lower one-sided bounds for the confidence interval on the mean. Okay? So what are these? Let's take a look at an example of what this might look like. And this might help provide some interpretation on what a one-sided confidence interval is, right? It's unbounded typically in one direction. So let's take a look at the following example. Suppose 25 students are selected randomly. And the reaction time in seconds to a stimulus is measured. 25 students are selected randomly, and their reaction time in seconds to a stimulus is measured. Past experience. Past experience suggests that reasonable value for sigma squared is 4 seconds. 4 seconds. This is to be variant, so this is 4 seconds squared. 4 seconds squared. 4 square seconds. And that the distribution is approximately normal. All right, almost done setting this problem up. The average time for the subjects, for the recorded subjects, is 6.2 seconds. Let's give an upper 95% bound for the mean reaction time. Upper 95% bound for the mean. Well, that's weird. I wrote mu for my m and mean. Getting subconscious clues here. The mean reaction time. All right, mean reaction time. So what we're doing is we're measuring the reaction time here. We don't care about the lower bound in the sense, or lower interval, because, you know, if the reaction time is 0, so what, right? But we are concerned with the upper bound and saying, well, how long, you know, can we put a cap on what the average is as far as an upper cap, right? Let's see what we know here. We know the sample mean x bar, 6.2. We're given sigma. If sigma squared is 4, sigma would be 2. And sample size, 25 students. 95% upper bound here, z. So 95% upper bound, so this is just z of 0.05 then, because it's a one-sided interval. Z of 0.05, let's go to the normal table and take a look. 5% to the right would be 95% to the left. So where is 0.950 here? 0.950 is 1.6 and split evenly between those two values, be 0.945. 0.9495 and 0.9505. So I would say it's fair game to say this is 1.645. So what's our upper one-sided bound? X bar plus z of alpha over 2 plus 1.645 times sigma over the square root of n. What's the square root of 25? Times 5. There we go. Run that through a calculator, and that is 6.858. This is an upper bound for the 95% confidence interval on the mean, right? We would say that we are 95% confident that mu is less than 6.858. And that's how we would interpret that one-sided bound. We are 95% confident that the mean does not exceed 6.858. And that is our one-sided confidence interval. That'll do it for this video. We will see you in the next one.